Okay, so this is a recording about Chapter 4 in your textbook, Combined Stresses and Stress Transformation. But before that, I want to refer you to a curved beam example. And this is you can see it has two curved areas. It's a shotgun and shotgun cock. And under the or during impact, there is a force that is generated acting like so, and we're going to see two areas of tensile stresses, one here and one here, as well as compressive stresses opposing. Now, what I want to say is, or emphasize, is that the radius of curvature here is less than it's here because the bending stresses would be less when evaluating the curved beam stresses in this area than it's here. It's simply because of the arm of the force. No, I want to use the line and make it. Let's make it a little bit thicker. So the arm of the moment would be only this much for the same force when evaluating the curved beam stresses in this area versus this much arm. I tried to make this 90 degrees. So bending stress will be more here than it's here. And it makes sense to make the radius of curvature wider because the stress will be less this way, where the moment is bigger. Yet another application example of curved beams and how they have been implemented in practice. So again, to accommodate or account for a bigger bending stress, the radius of curvature is bigger than it's here. For the same force, the arm is less here and it's bigger here, causing a bigger bending moment. Quick reference to the previous chapter on curve or section on curved beams. Okay, so combined stresses in machine elements, we oftentimes have the cases of combination of bending and torsion. It's common to shaft transmitting torque that are also subject to forces that are perpendicular to their longitudinal axis. They give the example here of an L bracket that is loaded, and we're going to see bending only over this portion as well as this one of the L brackets or the bracket bar. This other portion of the bar as well as this portion, they are subject to both bending and torsion. So we have a combination of loads, and one causes to an element that it's aligned with the longitudinal direction of this portion of the bracket. So one will cause tension and compression, talking about above and below, and then there's torsion that occurs the same on the outer skin, going to zero, same as bending actually to zero to the neutral axis. But one is axial stress, either tensile or compressive. The other one is tangential stress. And when selecting the material calculated design factor, you'd be curious to analyze or tell how is this combination of axial stress and torsional stress going to affect the ability of the material to resist loading. Okay, I sometimes make this analogy with a fighter, fist fighter, a boxer, that gets a punch in the face and a punch in the stomach, like 1-2 punch, face and stomach. What knocks the fighter down? Is it the combination of the two, the one in the face or the one in the stomach? So and this will be for later on when discussing failure theory. It may sound familiar to some of you. Von Mises stresses, I oftentimes see capstone project presentation by students, and they do analysis and report for Mises stresses. Sometimes not in the proper way. Okay, so in the most general case, three-dimensional element can be loaded with normal stresses, sigma x, sigma y. There'll be a sigma z, and then there are shear stresses on all surfaces. And there is a sign convention. I think we discussed this. So if the stress is away from the surface, it's positive, and it is labeled, or the index is that of the axis. If it's a shear stress, then first index is of the axis it intersects, and the second index is the axis along which is oriented. Compressive stresses are towards the surface. Here, all stresses are, or normal stresses are positive. There's a stencil. In practical problems, you won't see all stresses combined. Maybe in special circumstances, intricate shape parts loaded in with multiple loads along different orientation. One example that it's easy to comprehend is like performing a deep sea equipment that is subject, in addition to the loading required by the function it serves. There is also compressive stress. There are compressive stresses from all directions due to the hydrostatic pressure of the column of ocean water on top. In our analysis, many of these elements will look more like this. So you have shear stress, and shear is positive when it tends to rotate the element clockwise. So this will be positive, this will be positive, this will be negative, and this will be negative shear stress. And we know that on an element, these are equal in magnitude. Shear only has a rotational effect, or distors the element. But the net effect in terms of sum of force over x and y at 0. And then we have the normal stresses. Okay, so tensile, 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 tensile. This could be the case easily of a pressurized pipe. So due to the internal pressure, I have what will be, so assuming the pipe has the axis, x-axis, and very important, we choose the stress elements in a way that is it makes our analysis easier, to where the element is aligned with geometric axis of the part. So if we have a bar, we orient the element where the longitudinal axis of the bar is the x-axis of the element, the transverse, the y-axis, transverse axis of the element, and then go from there. It makes the analysis, because you're the one that you're going to evaluate or calculate sigma x, sigma y, tau x, y, or taus, and from there you want to find what how the stresses change as the orientation of the element changes. So I started saying that in a pressurized pipe, on the outer surface, you're going to experience axial load, the longitudinal stress. You will experience the hoop stress, and then if the pipe is also twisted, then there are shear stresses that occur. If that pipe is submerged deep in water, like thousands of feet at the bottom of the ocean, there will be a normal stress perpendicular to the outer skin. An element to the inside of the pipe, and the pipe, again, it's pressurized, is also going to experience a normal stress. Both cases, deep submerged or to the inside of the pipe, those are normal stresses, and compressive stresses normal to the element. Okay. So we discussed sign convention, and then the question is, what happens if I choose an element, so instead of being oriented with conveniently with the axis of the bar or pipe, I choose it at a different angle. And it makes sense, this kind of analysis makes sense, because we can have multiple situations. For example, different material respond differently to stresses. So these two are brittle materials. This is how the original specimen looked like in geometry. I cannot tell whether it's one of these three. So one, it's iron, aluminum, and this is a 1020 ductile low carbon steel. So subject to compression, the ductile material is just going to barrel. Cross section increases, less where contact it's made with the surfaces that it's compressing it. Explicable, there's friction that impends the increase of the diameter. But otherwise, the piece stays or the specimen stays in one piece. There's no fracture occurring. Remember comments that I made on different occasions that compressive stresses are not as bad as tensile stresses, particularly when talking about ductile materials, because the material stays, it doesn't separate. It's not going to break. It stays in one piece. There's a change of geometry, but it stays in one piece. It's the tensile stresses that we care, and again for ductile material. If we are dealing with brittle material, and this is an iron, this is an aluminum, you can see under the compressive stresses there is some plastic deformation. So there is an increase in diameter that is visible, so some ductile behavior. But fracture occurs, as you can see, about 45 degrees from the direction of the or axial direction along which the compressive stress is done. So different material responds differently to stresses. You want to evaluate the stress on an element that's aligned with, and it's 45 degrees. We'll see why. With an element that is rather long, so instead of being longitudinal, okay, so a stress element that's aligned with the longitudinal direction, it's an element that instead is, it's aligned with the direction about which we observe fracture, 45 degrees. Or maybe there's a repair, or it's a welded pipes. There are pipes that are fabricated by welding spiral sheet metal, long sheet metals. Think what? Toilet paper. The immediate example: toilet paper, the cardboard tube to the inside. Okay, or if there is a repair, there was a fracture and was welded, and you want to know what would be the stresses parallel and perpendicular to the repair. Okay. And other examples of this will be ductile tensile fracture. This is brittle compressive fracture, and not all materials, brittle materials, fracture this way at 45 degrees. Really, there are others that have different behavior. And then when it comes to torsion, now you have you twist a brittle material, and likewise you see it's fracturing at about 45 degrees. You can see, and instead of being just perpendicular to the versus the stud element, this is a little ductile aluminum alloy, and the fracture happens about perpendicular to the axis of twist. So all these explanation why this kind of analysis are important. So finding stresses on oriented elements, and then calculating what are called equivalent stresses. This will be for a little bit later in the chapter. Okay. So what happens if I am rotating an element over its original orientation where I had sigma x, sigma y, and tau xy. So if I take an element like this one, and instead I'm going to, let's see, there is a drawing tools, annotation, fill and sign, measure stamp, show more. Is this one? Oh, come on. No. So let's see. Cancel. No. Home. No, Mott Circle. Okay. Hey. A lot of things going on. I was trying to, sorry for this. So I was trying to show this element rotated by an angle. So the angle, it's measured from, let me pause and while I'm finding the tools. All right, sorry, wasn't able to find the annotation tool, the pencil tool. Looks like I need to pay $14 to get it. Okay, so yet again, I have the element oriented in convenient way to calculate sigma x, sigma y, tau xy. Now I want to know how these stresses change as I'm rotating the element. So imagine this square being drawn tilted by some angle, and this angle is measured from the x-axis. Okay, sigma x, it's aligned with the x-axis, and we call that angle phi, and we want to know how that angle influences the normal stresses and the shear stress on the rotated element. And these are equations. They are derived in this chapter 10 from the Strength of Materials book by the same author. And if you have that book, you want to go back. Things are explained in much detail, including the derivation of those equations. In addition, it discusses the principal superpositions when stresses are in alignment. So we had, and we looked at this kind of problem where bending is overlapped with tension, and you just add the stresses as collinear vectors. So there is this part of the chapter in the chapter 10 of Strength book where the relationship between stresses and the angle of rotation are explained by looking at the equilibrium of a portion of the original stress element. So it has to be in equilibrium, and slowly the equations that are presented directly in the in our book are derived, but we have them here again available. As you can study the effect of, or rather, when these stresses experience minimum and maximum values. So you take the derivative with respect to phi, and you set the derivative equals 0, and it gets us the equation for the maximum. What's the angle for maximum if we take derivative of either this or this one? And of course we take derivative with respect to phi and find where the maximum or minimum of the shear stresses occur. Okay, so for the first two cases, when the normal stresses have minimum maximum values, we find the corresponding phi, we substitute it in the original, find the original equations, and it gets us what are called principal stresses. So these are the principal stresses, and we like to report them as sigma 1 bigger than sigma 2. Okay, and then using this equation, you can even calculate the angle, how put a value to it. And here it shows the example of a principal element is called. So principal element because I have maximum normal stresses and there's no shear stress. So very important, on the principal element where we have principal stresses, there's no shear. So again, by simply by rotating the element, we can find orientation of the element, an angle phi sigma where there's no shear. Okay. Now, likewise, we want to know when, at what angle we are going to experience the maximum shear stresses. And for that, we take the derivative, was I said earlier, was phi of the third of the equations, and it's this is the result, and we get the substituting back in the third equation gets us the maximum shear stress. Okay, and the angle for the maximum shear stress. If we look at the two, we see that, just look carefully, so you see that it's flipped, and with the change sign, so it's indicative that the maximum shear stress occurs at an angle that is 45 degrees rotated either clockwise or counterclockwise or clockwise from the principal element. So the principal element and the element of maximum shear stress are 45 degrees apart on one hand. And then secondly, another property of the maximum shear stress element is that the normal stresses are equal in are equal in magnitude and equal to the average stress. Okay, so the average stress being sigma x plus sigma y divided by 2, or could be also sigma 1 and sigma 2 plus sigma 2 divided by 2. So this important conclusion that the angle between principal stress and element and maximum shear stress element always 45 degrees. So if we go back to these figures, or maybe this one. So this was a tensile test, and fracture occurred at 45 degrees. That was it corresponds to the maximum shear stress element, orientation maximum shear stress. So the longitudinal direction, it's a principal axis also called. So we have maximum tensile stress, 0 normal stress to an element. I can't even draw it. So I take, it should be a square. So I take an element, and when in tension, I have, come on, okay, so, and then likewise, nope, now you go to this other one, and they were supposed to be centered. Alright, so the sigma is force, tensile force, which is axial force, divided by cross-section area, is going to give us the principal stress, sigma x, if x is the longitudinal axis. Sigma y is going to be 0. And now the maximum shear element is going to be at 45 degrees. So it looks like for this material, failure occurred when we reached the shear strength, the maximum shear strength. Okay, so let's go back to the chapter. There are instances where stresses occur not just in plane but three-dimensionally, and for that case, we can calculate the three principal stresses, all in the most general case, all non-zero, and they are the solution of this cubic equation with the coefficients C2, C1, C0, C1, C2 as shown. Again, we like to report principal stresses as sigma 1 the largest, sigma 3 the minimum, and sigma 2 in between. So these are the principal stresses. Okay. The book continues, summarize the steps. Feel free to go over the chapter at your own pace, and also study the sample problems. Like this one here. This one here shows a torque transmitting shaft between two pulleys, and because of the tension in the so two belt transmission, because of the tension in the belt in the horizontal plane, which is XZ plane, we have bending. Okay, so the shaft is going to bend, if you want, this way. And in addition, between points B and C, we're having torsion because there's torque transmitted between these two pulleys. Areas of interest, and this is a rotating shaft, and you'll see next chapter. This is a fatigue analysis problem. But thinking static loading, areas of the shaft of interest would be to the inside. It is on where the z-axis or parallel to it comes out of the shaft. So this is where we have maximum tensile stress, and overlapped with it we have the shear stress caused by torsion. On the opposite surface to this one, where the negative z-axis exits, or parallel to it exits the shaft, we're going to have compressive stress, maximum compressive stress. Again, because of the bending stress distribution going from maximum on one surface to negative to maximum to the opposite surface. So on the opposite side, we have compressive stress caused by bending, as well as shear caused by the torque. We can calculate both. We know how to do it. We can find reactions and supports. We can draw shear force and bending moment diagram. We take the maximum bending moment from the diagram. Torsional stress is the same between the two pulleys. Bending stress is going to max depending on the magnitude of these forces. Let's see. So yeah, it's going to max right at B. Okay, and just a digression. This is where things get complicated, because we have singularity like keys, and how it's going to go from maximum torque between B and C to no torque right opposing to. But conservatively, we were assuming that maximum bending moment at B, it's associated with maximum was the maximum shear stress caused by torque, to be on the safe side, and even account for stress concentrate caused by the keys or splines if there's, and they should be present to transmit torque from the pulley to the shaft. But again, we have the tools. We know how to calculate the shear stresses when we know the torque. We know how to calculate the maximum bending stresses when we know the bending moment. And we have, once we correctly orient the stresses on the element and put values to them, we can apply the earlier equations. Okay, so we can apply the earlier equation and calculate sigma 1 and sigma 2. What do we do with sigma 1 and sigma 2, as well as a tau max? Well, the first thought is, let's take the maximum sigma 1 and compare it with the yield strength, and decide whether a design factor is satisfactory or not. But again, depends on the element, on the material of the shaft. Some may fail when the maximum shear stress reaches a limit. So we don't have an answer yet. The rest of or later in the chapter, we'll learn how to further utilize these principal stresses, the calculated principal stresses. Knowledge about the angle at which the orientation, that is, of the principal element, it's sometimes but not always important as the principal stresses. Okay, and for a thorough analysis, it's useful to show the relative or how they position relative to each other, the original element, the principal stress element, the maximum shear stress element, and at what angles these occur. So other than using the equations, the equations that we learned at the beginning, 4.5, 4.6, and this other one, 4.9, there is a graphical method widely used by engineers, which is Mohr Circle. And Mohr Circle is also introduced in chapter 10 of the strength book. So if you still have the strength book, you may want to go back to it and read there too about Mohr Circle. It might be better explained. But again, Mohr Circle, it's a graphical method of keeping track of these stresses, finding the directions of the principal element relative to the stress element, as well as calculating stresses of an element at any angle relative to the original, the direction of the original element. Okay, so how is this working? We draw a reference orthogonal axis, sigma x, or at the sigma positive to the right in the horizontal axis, and tau, the vertical axis, positive would be clockwise and will be up. And then we calculate, we locate the center of the circle, and the center of the circle, it's on the sigma axis at sigma x plus the average. So you add sigma x and sigma y divided by 2 gets you where the origin of the circle is. And then we can show a diameter of the Mohr circle, and also calculate the radius of the circle. So 2.2 two diametral points would correspond to sigma x tau xy and sigma y tau yx, which is negative of tau xy. But otherwise, we can locate these points by moving the amount a, and a is going to be sigma x minus sigma average, and then b is going to be tau xy. The radius of the circle is going to be square root of a squared plus b squared, Pythagoras theorem. Okay. So again, we have 2 points, two diametral points, and we can draw the circle if you can follow the mouse cursor. So you draw the circle. Okay. Having the center and the diameter or the radius known. Very important. The x-axis of the original element will have this orientation. The principal stresses now, sigma 1 and sigma 2, you're going to get them by intersecting the circle with the sigma axis. So again, we got the circle, we got the two diametral points, we drew the circle, we have the radius. Sigma 1 would be the intersection of the circle with the sigma axis. Sigma 2 is the other intersection. And sigma 2 may end up being negative or could be also positive, it depends. And then we have tau max, and tau max is going to be equal to, as you can see, the radius of the circle. So you take the top quadrant, bottom quadrant, draw a line, intersect the tau axis, that's the tau max. and the 2 points, they have the coordinates. Sigma average, of course, is on top of the center and right below the center. And for the y, like I said, it's tau max. So yeah, easy to get sigma 1, sigma 2, and tau max on one hand. And then we can also tell the amount of rotation that we need to perform. So again, the principal element, it's shown here, oriented with the horizontal and the vertical lines, like they come out from our choice of the axis. And you go back. So again, it was convenient to align the principal element, or rather the original element with the direction easy to position on the original part. But from there, and seeing that the x-axis on the Mohr circle grows from origin in this direction, if I rotate the element half of this angle. So one thing about Mohr circle is that on the drawing for Mohr circle diagram, for Mohr circle diagram, angles are twice as big, and to get the principal axis, I need to rotate the x-axis, that is the element, half of this angle, and that will give me the principal element. If I rotate, that is half of this big angle, that it's labeled 2 phi sigma, and this will be clockwise. If I rotate the original element counterclockwise, half of this angle, this full angle, or which is labeled 2 phi thou, I'm going to get the maximum shear stress element. Okay. In chapter 10 of the strength book, there's less emphasis on what is called three-dimensional Mohr circle. We like to do a complete diagram by adding. So here I have sigma 2, here I have, or sigma 1, the principal stress, sigma 2, principal stress. Actually, assuming non-zero normal stress, or rather zero normal stress to the element. So again, the plane would be x, y, the z-axis now, no stress along the z-axis. That will be a principal stress, and I have it is 0 shown on the graph, and these 2 circles shown. So add the third of the stress on the graph, could be 0, other than on pressurized pipe to the inside, or on loaded elements that are pressurized, submerged, again deep undersea. So other than those cases, the z-axis stress, sigma z, is going to be 0. It's shown here on the graph. Labeling is redone. I have sigma 1, sigma 2, the value in between of the 3 principal stresses, and this will be sigma 3. Okay, so this is the 3D Mohr circle. Okay, so everything that we discussed, they're listed here as steps to follow. I would recommend you to understand and study clearly, and even bookmark page 151, and you come back to this, and you can draw Mohr circle. Remember the additional step of showing the third of the principal stresses, which is sigma 2 in this case. Again, if we do just 2D circle, it will be sigma 1, sigma 2. Otherwise, notations change to accommodate for sigma 3 as being the lowest of the stresses. Some examples, and they are just listing sigma x, sigma y, tau xy as values, various combinations of values, and draw Mohr circle with those. Okay. The more relevant case with third stress with 3D Mohr circle is when we have sigma 2, or the sigma 1 and sigma 2, the principal stresses, principal two-dimensional stresses, being both positive. Okay, and this is yet again the case of pressurized pipes, because we have on the outer surface, remember there's the axial stress and the hoop stress, both positive, and if we don't introduce the zero stress perpendicular to the surface, outer surface of the pipe, we're not discussing yet the case to the inside where sigma 3 is actually negative and equal to the pressure that is inside of the pipe, or the pressurized cylinder. So we have or introduce necessarily the third stress, even if it's zero, and we have a circle that is going to have the largest radius of the two, and that's going to give us the maximum shear stress. Okay. So there are cases in a listed pressurized pipes or normal stresses because of pressurized pipes, either to the inside, to the outside, or parts of machines that operate submerged at high compressive stresses due to the hydrostatic pressure under the sea. It's relevant, very relevant, very important to add or do 3D Mohr circle analysis. Okay, so what do we do with these principal stresses? Or with the maximum shear stress, the way I said, it's identified only by showing 3D Mohr circles for pressurized pipes, for example. We can apply what are called failure theories, and one is, it's called Tresca stress. Some refer to it as just maximum shear stress theory, and we relate. Remember that you look at here at sigma 1 minus sigma 3 divided by 2. That's actually the radius of the largest of these three circles. It's called sigma prime, but that's a shear stress. And you compare this stress, the radius of the major of the three circles, to the shear strength of the material. Most widely used with ductile materials like carbon steels is this von Mises equivalent stress. And you calculate it. It comes from what is called maximum distortion energy theory. You calculate it with this equation. You found sigma 1, sigma 2, and sigma 3. You're using this equation 415 to calculate the von Mises stress, equivalent stress, and you relate it with the yield strength of the material. Okay. So the limit case is where the two are equal and means that failure is impending. Of course, everything is probabilistic. So we have the yield strength is not a strict value. Depends on the, for a given steel grade, depends on the batch and how was individually treated. But in general, so if we have equal sign, then failure is impending. As you know, we want to have some margin that is yield strength to be greater. It's where design factor, 175.2 for static loading. Bigger the yield strength. Otherwise, here it says failure occurs when the equivalent stress is greater than the yield strength. Okay, and there are some practical problems. Various combinations of sigma x, sigma y, tau xy, and careful application of the steps in boxes. And that earlier figure that I told you to bookmark, good understanding of this figure, 412 Actually, the particular cases are sometimes more challenging or confusing to the student. And these are several discussed here. So, special stress condition. If we have pure axial loading, this is already a principal element. So we have sigma x is going to be sigma 1, sigma, and it's a 2D circle. Sigma 2 is going to be sigma y equals 0. And maximum shear stress is going to be the average. So you have sigma x plus sigma y divided by 2. That's sigma x divided by 2. This is how the circle looks like. And you can see they made it 3D circle because it's represented they're on the circle both sigma 2 and sigma 3 as being 0. Again, sigma 3 is the stress, normal stress in the z direction, which is inexistent if it's an element in the ambient pressure and 1 atmosphere pressure. For compression, the image is mirrored. We have a negative sigma x, sigma y is 0, sigma z is 0. The circle looks like this one. The maximum shear stress would be the average of the principal stress, sigma x divided by 2, essentially. Biaxial tension comes to mind. Again, the pressure vessels was longitudinal hoop stress. Hoop stress is for pressurized pipes and cylinders is twice the longitudinal stress. And here's where I said the 3D circle is useful to be drawn. So for some reason, pure uniaxial compression was the above case. Axial tension, yeah, they took the particular case where the two are equal. Again, the particular cases where we have they're a bit more you require careful a bit more careful analysis. Okay, and then for pure shear, the element is oriented with the tau axis, and we get the principal stress sigma 1 and sigma 3, with sigma 2 being 0 is the normal stress, the z-axis stress. So sigma 1 is tau x x1, and then here we have shear stress and axial stress. Think of a shaft that is in bending, and we have the tensile part side of the bent shaft, and the shear caused by a twist, by torsion. Depending on how these get combined together, so for maximum shear stress, if we get the minimum stress, the negative one, less than 0, is the case. Yet again, the usefulness of showing the 3 circles, recognizing one of the principal stress of being 0, and this is for finding the maximum shear stress, which may be the one that is the most detrimental to the material of the component. Okay, there is, and we'll do our own share of examples of problems. The torsion and shear, same as in the strength book, just because we have tension and shear, tension being possibly caused by bending, it's so common in power transmitting shafts, like the one with the 2 pulleys that we saw earlier. So it is analyzed here separate, and we know how to find on one hand, given the torque and the polar section modulus, how the magnitude of tau xy, and then the bending stress, it was listed here, M over section modulus S rather than MC over Y, the flexure formula. And when calculating tau max, we recognize and for solid bar, solid circular or cylindrical shafts, we recognize this component here, which can be treated as an equivalent torque. Okay, so bending moment and the torque loading the shaft squared and square rooted gets us an equivalent torque. And again, given the wide or numerous cases of this type of loading, bending and or tension caused by bending and shear caused by torque, we can analyze it quickly using the equivalent torque. Okay, I kept on mentioning some of you may have studied pressure vessels in, probably not, in strength of materials. We're going to look at that chapter in a separate recording. We have cylinders and pipes that are pressurized, and I mentioned longitudinal stress and I mentioned hoop stress. They have the direction, assuming the element to be, and it's the way we like it, line with the longitudinal axis of the shaft. And how do we calculate these two stresses? The longitudinal stress is just going to be the inside pressure multiplying the projected area, transverse area of the pipe. Gets a force that causes the pipe or the cylinder to stretch. And then for the hoop stress is twice as big. So we have I start with the longitudinal stress. Here's the formula for it. So inside pressure, diameter of the cylinder. It says mean diameter of the cylinder, and then divided by 4 divided by thickness of the cylinder. And for hoop stress is twice as big. You see here it divides only by 2, so same terms, but it's a 2 instead of a 4. This applies correctly for thin wall cylinders. So a thin wall cylinder is one where the diameter, mean diameter over thickness, is greater than 20. We'll look at that by studying chapter 12 from the Strength of Materials book by Mott and Unterner. Okay, so like I said, mean diameter divided by thickness, that makes it a thin wall cylinder for this sample problem. Again, the element is oriented longitudinal, its position longitudinal to the cylinder or to the pipe. Where I'm going to look with you as cases where if the pipe is also subject to additional loading, like caused by bending or by torsion. This is about it. This is the chapter. Again, there will be a separate recording for pressure vessels. We've been already exposed or introduced. Here's a review just of the equation for thin wall cylinders. Are also going to look at thick wall cylinder as well as spherical pressure vessels from chapter 12 of Mott's book. Okay, so this is it. I'm stopping recording.